So today, let's go through Lab 7. A couple of people have requested to look at the remaining problems in Lab 7. That's problems 2, 3, 4, and 5. So let's go ahead and do that today. So the first problem was to implement binary search. So we get a vector v and an element k. We need to determine whether k is in v or not. We return true if k is in v. We return false if it's not. And we use an efficient algorithm called binary search to do that. Let's look at some other problems. Here's exercise 2, finding the maximum value in a 2D array. So here we have a function called findMax. And the function takes, this should be double. The function takes a single argument, which is an array that's specifically sized to rows, and columns. Let me show you what that might look like in code. So we don't have a vector in this problem, so I'll take out the vector class. So this is an array. And I'll just take this out. This is just the shell from where we start from. This is the main program. Let's see if we can compile that. Should stay all tests passed. Looks good. And then our job is to implement a function that looks like this. But this should be doubled, not double. Now, this won't compile because rows and cols are not defined. Undeclared identifier, rows. So let's define that here. We can define it as a const int rows equals, whatever it is, like
I need to pull it, Daniel.
3. And look, we also need to define calls. Say we'll call that 2. So 3 rows and 2 columns. Now this should compile, except we'll get a warning here. We need to return a value. Let's return 0. See, this function is declared as returning double. So we're just making sure that our stub builds at this point. Looks good. All right. Provide test code that defines an array of size rows by calls and that uses an assert statement to check that the function returns the correct value. So let's go ahead and define an integer array with some test data in it. And here's one way to do it, I think. I'm just going to try this to see if it works. So we have 3 rows with 2 values in each column. Just some test data. I'm just going to make that a little neater. So the way I have it coded, it's this is a semicolon, I think. And the way I have it coded, I just tried to make it to sort of easy to visualize as rows and columns. Let's see if that compiles to make sure the syntax is right. It doesn't look good. So what is the issue there? It says excess elements in scalar initializer. Oh, this should be a two-dimensional array. Still is not right. Something like this. That doesn't work either. Let's do it like this. Ay, 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 ay. How do you do this? Oh, that's not right. There we go. It accepted this syntax here. Now we call find max. We pass in A. Well, we have our stub returning 0, so it should just print 0. No matching function for call to find max. Oh, that's a double. The data type is double. So I'm passing in, I declared A as a two-dimensional array of int, and the compiler said you can't pass that in to find max. It didn't say that, it said I can't find the function called find max. It takes a two-dimensional array of int. So we need to have matching data types there. It prints 0. There we go. But we want to express this with an assertion. Assert find max is 0. All tests pass. But actually, the maximum value is 44. So find max should return 44. So now we'll make the program fail on that assertion. There we go. Good. So now we have the test code set up. Let's go ahead and implement the function. We need to scan through this array. So it's a two-dimensional array, so we'll need nested loops to do this. Oh, there's other ways of doing it, but this would be the most obvious way I'm showing you. So we'll declare integer I started at 0. I needs to be less than rows. That's plus I. And the same with J. But J stops at columns. So we'll have a variable at the very end. We'll return the will return the max. I'll call it, maybe I'll call it max value. I don't want to call it max because there's a function called max. I just want to avoid confusion around that. Well, we could call it max. Yeah, maybe we'll call it max. We'll see what happens here. So we need to define max. The function returns a double, so max needs to be a double. And we'll have to initialize it to something. What do we initialize it to? Well, I can think of a test case where we have to be careful about that. What happens if we set all of the values in the array to negative numbers? I did that wrong. This should be like this. Suppose we had a bunch of negative numbers in there. The max should be minus 20. That's why if we initialize max here to 0, we search for a number that's bigger than 0, we'll never find it, and then we'll return 0. So that would be a problem. And we just, because the thing is I realized that was a problem as I was coding. And what did I do? I wrote a test case to test against that problem. So this is a type of discipline called test-driven design or test-driven development. Right, in that strategy, you write your test code first before you attempt an implementation. Of course, the test code should fail. But I'm going to leave this 0 here in order to trigger the failure of the second test. And then once we get the first test to pass, we get the basic algorithm done, then the second test will fail, and then we'll go back and make that adjustment. So we're being very deliberate about how we're writing our test code. So what do we do in that loop? Basically, we're looking at every value. So I and j are ranging across all valid indices. So for each valid index, pair of indices, we're going to compare the value at that location with our current record of what's the largest thing that we've seen so far, which is the value of max. So if a of ij is bigger than max, then max gets a of ij. Maybe that's hard to read. Let me do it like this. Maybe this is easier to read. I don't know. There's a lot of indentation there. And too many indents are hard to read. So if aij, so I think I'm going to get rid of that indent. I'm just going to, because it's only one statement, that needs to run if the if condition is true. So this cuts back on the indentation a little bit. So this code should pass the first test but fail on the second test. There it is, find max equals -20. That's the failed assertion. That's the second test. But the code that we've written is sufficient for this test case. This two-dimensional array, find max returns 44 as it should. But the second test case fails because here what we've done is set every value in A to -20. And the max should be -20. However, we never replace, we set max to 0 here, and we never replace it with anything. So actually, a better starting point is to set the max to the first value in A. That way we know we're starting at a known point. And if all the values after A are less than A, then the max will be, if all the values after the first element are less than the first element, then we'll return the first element. There it is, we got it. So there's the solution to the problem. I had to guess around to get this syntax. This array is a fixed size, which all arrays are. All right, any questions? Otherwise, I'll move on to the next problem. Okay. Linear search. We're going to compile ex3.cpp and run that. So linear search. So we need to do, if the elements in a sequence are not in order, then we cannot do binary search. We cannot do the fast search. It's as if we had a telephone book where all the names were not in alphabetical order. They were just added in a random fashion. So if we wanted to look up a phone number in that book, we would start naturally at page 1 and go forward one page at a time, looking at each entry in the book, one after another, sequentially. As you can imagine, that's a lot slower. That's called, that's a linear search. So here's the function we need to implement. Implement a function that searches for a given value k in an array of integers. Do not assume the values are in order. If the value is found, the function returns the index of the value in the array. So we want to know the position of the value we're interested in. If we don't find it in the array, if we don't find k in A, then we return -1. -1 is an invalid index. Array indices can only be non-negative. And here's an example, and we'll use this for the test code. There's an array of 5 elements, and we're looking for 1. The function doesn't find 1 in that sequence, so it returns -1. When we try the function again with 4, it'll return 1 because that's the position of 4 in the array. 4 is in position 1, which is the second position. The first position is position 0. So labeling of positions in arrays start at 0. All right, let's do this. And let's use the test. Let's write the test code first. And I'll complete this, this stub here. So we're going to return 0. That's the first position. Actually, let's return -1. That means we didn't find it. So we have an integer, an array A, which equals that sequence of values. We're going to call search. Sorry about that. I'm going to pass in A and 4. Was it 4? No, it was 1. The 1 is not in A, so search should return -1.
But your constructor is set off with 3. Will it work with just 2 values?
What's that?
Sorry, just go on. I'll catch up.
Yeah. Oh, we have the second argument here, size. Thank you. The size of A is, thank you, 5. The size of A is 5. I have to pass in the size of the array as the second argument.
So this wouldn't work with vectors, would it?
No, well, we can rewrite it. It's the same algorithm with vectors. We don't need to pass in the size of a vector because that's a function that we can invoke on the vector. The vectors are more convenient. In general, vectors are more convenient to work with than arrays. Yeah, the code can be more compressed, but the algorithm is essentially the same thing.
Okay.
So be prepared on the exam. I can ask this problem to you and state it in terms of vectors rather than arrays. So you would have to know how to code this out on the exam using a vector rather than an array. Thanks for that idea.
Damn. Sorry, guys.
All right, and then we have another, let's try, when we search for 4, it should return 1, rather. That's the, see, 4 is in position 1 right there. This is position 0. This is position 1. So search returns the index of that value in the array. So 4 would be found at index 1. So search returns 1. So we assert that search equals 1 when we call search. Now we're already just returning -1 here. So the first assertion should pass without doing anything. The second one will fail. There it is. That's the second assertion. All right, let's go ahead and do this linear search. Basically, we need to look at every value in A. So we'll write a for loop that computes every valid index for the array. So this is a pretty standard for loop. A lot of for loops look exactly like this. So now, for the index I that we have, we want to see if the value at I, A of I, equals the value we're asked to look for, which is K. So if the value at I is K, then we found it. So we return what?
1. No, wait,
Return I.
Yeah, exactly, good. We return the index. That's what the problem asks for the position. The function returns the index of the value in the array. Otherwise, it returns -1 if it doesn't find it. And by the way, that's a typical return value. Now, all the different APIs, all the different languages, this is how you would do it. By the customary way to do it is you return -1 to indicate the value is not in the sequence. Otherwise, you return its position value, considering the fact that the first position is labeled 0. All right, so that should do it right there. There it is. Now that's good. That's good enough for that problem. And you see that the two test cases that I have here, I'm checking every route through the code that's possible. You know, in one route, I return from this point. And the other route, I return when we exit the for loop, we haven't found k. So it's not there. We looked at everything. So let's return -1. So that there's two corresponding test cases for that, for those two different pathways through the logic in that function. And that what we say there is we use the term coverage. The test code has good coverage because it executes and validates every line of in the function that we're testing. Okay, exercise 4. More binary search. I'll start with 1. So this is binary search, but it's just the function is packaged in a different way. In the first problem, we return a bool. We say, hey, just tell me true or false is k in v, where v is a vector. This is another version of binary search here. But here, we're not passing in a vector v, we're passing in an array of int a. And we're saying, don't tell me yes or no whether you found it. Tell me, I want to know where it is. So give me the index, just like the problem we just solved. This problem wants you to compute or return the index of the value k in the array A. So I copied over the code from exercise 1, because it will be essentially the same. And we have the same test code that we had for the other one, actually. We're not using vectors, we're using arrays. So there's one test. And we're testing k equals 1 and k equals 4, both of those. Actually, I'll just get these. Well, this will be binary search. So this, when we search for 1 in A, it doesn't find it, so it should return -1. But when we search for 4 in A, it finds it at position 1. So we check for 1 there. We've got our test code in place. And I'll just for the time being, I'm going to comment all this out.
Since we're working with arrays, do we still need the pound include vector and the v
No,
dot
we
size?
don't. Thank you. And that should be deleted. That's very, but that is distracting and confusing to have an include directive for something we don't need. Thank you for that. So now I commented this code out, which is written in terms of vectors. And I turned the function into a stub that just returns -1. I just want to make sure that the test code is set up. And the first assertion will succeed because we're returning, the stub returns -1. But the second assertion will fail because the stub returns -1 and we check for 1 as a return value. So let's see that that second assertion fails. Hopefully the code will compile, and it does. And it says all tests passed, and I compiled the wrong program. It should be 4. There it is, the second assertion failed. All right, so we have an algorithm already in place here that is written for vectors. We just need to port it over so that it's written for arrays. I'll take these comments out. And we have the same starting position and the ending position. We can't use v.size. We don't have v. But we know the size. The size is required. It's not a part of an array object in memory. It has to be maintained separately. And so we pass it in as a second argument. So we just use, rather than v.size, we'll just use the variable size. That's it. Oh, that's not it. It's not v of m. We changed the name to a. So the syntax for accessing a value in an array, these square brackets, is the same syntax for accessing a value in a vector. Let me clear the screen here. Compile and run. That's good. One more to go. Guess the number.
So this one was like number 1?
What's that?
This one was like number 1?
It's like number 1, except this returns an int, which is the position. Oh, this is wrong. Look at this. This returns true. Well, you know what? True is turning out to be 1. Look at that. The test code is not good. I felt there was a problem with using this 1 here. Let me show you. Let's check for 18. 18 is in position 2. Right? '18 is in position 2. So look, the problem here is that we're returning true here, and the compiler accepts it. It's actually in C++ and in C. The data type bool is just internally represented as an int. And an int and a bool can be used interchangeably in your code. But that's not true for other languages. It's not It's considered a weakness in this language, by the way. It's an old language. All these weaknesses in old languages don't appear in newer languages because they're weaknesses and they've been understood as weaknesses later on. So we can see the weakness already. The test code that we had is actually not good enough to detect this, this mistake, this bug. So we just, rather than fixing it, look at the discipline. This is a test-driven development discipline. Rather than just fixing it, I create a test case to fail on this. And then once we get the test case to fail, then we fix it. That's the process. Interview for a job and explain that to the interviewer, and you'll get the job. Okay. Look at that. The test code has revealed the bug. It's actually returning 1 because it's returning true. This is what it's returning. And look, there's no warning. So what do we replace true with?
A of I.
We want to return the position of K in A. A is an array. We need to return an integer, a position. We know K already. We passed it into the array. We don't need to get back what we passed in. M is, we found it. K equals A of M.
Oh.
M is where it is. M is where K is.
Okay.
There we go. See, I didn't catch that, Yvette. You started asking some question about this, and then I caught it, and I saw, oh, yes. See how our first pass at the test code was actually pretty bad. I mean, we missed this. Right, we missed this. That's why you need to be careful about testing special numbers, like 1 and 0 are special values. Okay. All right, let's move on and do this guess the number game. Now, guess the number. I put it in here because essentially, you know, the best strategy in a guess the number game is to use binary search. So you use it as a user, as a game player, that you use binary search. So the computer is thinking of a number, and your job as a user is to guess what that value is. And it'll let you try over and over again. So write a program that implements guess the number game. The program should enter a loop that starts by printing what is the number. After printing this, it reads the user response. You see in input operator n to read the user response. If the user enters a value less than 1023, the program prints too small and continues the loop. If the user enters a number larger than 1023, the program prints too big and continues the loop. If the user enters the number 1023, the program prints you got it and terminates. All right, let's try this. This is 5, right? What is the number? Look at this. Anybody know what's going on?
You need some input validation.
No, it's
Inputting
it's
from-
harder to understand. This web page. Look at that nice little quote there. See how that looks? This is like angling down. This
Oh,
one
you have to have
angles
a-
up.
Backward or forward slash one of the two, and then have the quotation marks. Because the compiler's thinking you're ending the code at those parts.
No,
So
no,
it's
no,
not
no.
gonna print the quote?
It's not that. This I want this to be a string. I don't want to print the quotes.
Oh.
Yeah, so-
And if I type in this quote, well, not this quote here. Wait a minute. There it is. You see it visually, how those are different?
Yes.
Well, I copied this one from the web page, and it's using a character set
Oh.
that represents this fancy, nicely typeset quote, which is a different character internally than what the compiler needs to have.
So don't copy and paste your code.
Exactly, don't be lazy and actually type everything out.
No, I think lazy is good. We'd want to type everything out if we can, but this is a problem. It's something to be aware of. See, we don't see it. We can see it visually here, but actually in some systems, we wouldn't be able to see the difference between those two quote symbols. And then it would be very difficult to understand this. Look, it's not bad. Look at the error message. Non-ASCII characters are not allowed inside of literals and identifiers. Outside of literals. Look at this. What if we did this? Are non-ASCII characters allowed inside literals? It said outside literals. Oops, not that one. See that? So these are non-ASCII characters. So I believe that the C++ language only allows for ASCII characters as part of its language. I mean, what's on the inside of a literal, that's just data. So it could be anything. But the language elements, like the string delimiters, quote, that has to be an ASCII character. It can't be one of these, special, designer characters here, designer quotes. Do people understand this? It's kind of hard, actually. In the old days, characters were represented with single bytes, which are 8 bits. So there's only 256 possible states for 8 bits to be in. So you can have a maximum of 256 different characters. The original computers could only have 256 different characters stored in strings. But there's languages that have more than 256 characters, like obviously Chinese and several other languages. And so it's inadequate. But not only that, but there's special symbols that we'd like to represent. These quote marks are part of the special symbols and so on. So the more things you wanted to represent, we just, they ran out of space, essentially. But original designers of computers weren't thinking about the future in the way it would evolve. Otherwise, I think they would have maybe chosen to use 2 bytes to represent characters, which is what some systems. I don't want to get into it. It's a really complicated and messy subject, how to represent characters. We call these different character sets. So on web pages, generally you have one type of character set that's different than, say, internally inside the operating system as a Unicode has a 16-byte character set, But on web pages, you tend to use, what's it called? I forgot the name of it. What's the character set for web pages? It's like, I forgot what it was called. It was the variable length representation of characters. I'm just going to look that up here. Oh, UTF-8 right here. There's the char set. See this meta tag right there? So this is a statement of what the character set is. So this is UTF-8. That's a big, all-embracing method of representing everything. So we could embed Chinese characters in there and all kinds of stuff. Actually, it will look like this. Let's see if we can get a Chinese character. So do something like how do you embed a value, an ASCII, a hexadecimal value? Is that right? Not sure that's going to work. Does something. I'm not sure. How do you, and let's see and see.
What are you looking to do?
I want to embed a 2 bytes, kind of an arbitrary 2 bytes inside the middle of the string. What's the syntax for that? For character literals, maybe this. Oh, like this. This is Unicode here. Oh, yeah, sorry, UTF. This is UTF-8, looks like that. This is UTF-16. And so we could do something like this. Anyway, it has examples, I'm sure, down here. So let's do U with 4 X's. There it is. So, you know, there's lots of different characters that this console actually can render for us. And that's what's going on anyway. I don't want to spend any more time on that. What is the number? I'm going to get rid of these quotes and just use the legal ones. All right, so what's the number? And we'll have a loop. I'm just going to start with an infinite loop. And in the infinite loop, we're going to read a value into n. Let's declare n as an integer. If n is less than 1023 rather, then we'll say that it's too small. Else, if n is greater than 1023, we'll say it's too big. Else, what do we do here?
If n is equal to 1023.
We can do another else if, but actually, if these are both false, it must be the case that n is 1023. So we can express that with an assertion. And that checks our reasoning, by the way. And this assertion, the code for the assertion is omitted when we do what's called a release build. You could sprinkle lots of assertions through your code. They slow things up. But when you do what's called a release build, you can have the compiler omit all those calls to assert. So let's just throw that assertion in there just to check, just to verify our reasoning at this point. And what is it that we do at this point? Well, they got it, right? So we're going to see out, we're going to say, you got it. You get it. So you got it. They won the game. And we'll also, we can just throw a return in there. So we have an infinite loop, say. The only way to break the loop is to guess the number and then execute that return. So this is a non-void function, so we need to return, we return 0. See, now main returns an int. So this is called the entry point to your program, the main function. So when the compiler builds the code, it says where, if we don't list a main, it'll complain about that. Let me show you this. Called this main X. So main is no longer defined. It's the linker actually will complain. Main, undefined symbol. See, it's looking for main. Implicit entry start for main executable. See that? So it needs to find a main. That's called the entry point. And now when you return from this entry point, you're passing control back to whatever process started your program. And that process wants to know whether the program is terminating normally or terminating abnormally. And so that's the reason we return an int. We return a 0 to indicate that the program is terminating normally. And we return a non-zero to indicate that the program is aborting, that there's been a problem. And we could return different values to represent different error conditions. But if it's non-zero, it means it's an error. And so system administrators write scripts that check the return codes of programs that they run. And sometimes you'll look for this return code. If it's not a 0, you'll halt execution of the script. So your script may be a sequence of program invocations. And at any point in that sequence of program malfunctions, you stop at that point, you halt. So these outside processes that launch your program will look at that return value, take action accordingly. But you know, this game isn't very fun for us to play ourselves, is it? So if we randomize it,
As far as like input validation, how do you make sure you enter a number? And
I'm not going to cover that.
No.
Yeah, I could pass this in. It's an infinite loop, actually. I can cover that topic if you want. I'm not going to test on it now.
Are we gonna keep the while true? Or do you wanna?
Yeah, this is okay. But here, you could test, I'll do it really quickly. If cin.fail, if cn is entered into a fail state after we do that input operation, then we'll do something like this. That input. And then we'll return 1. Say that it failed. Let's see if that fixes this. What's the number? See that? We got to run it again to try it again. So what we could do is modify this. Instead of returning 1, what we can do is do continue, which is start from the start of the loop. Oh, didn't work. This says continue. Ah, what we need to do, we have to clear I think we need to clear C and something like that. Let me try that. That's not it either. How do we clear the C in?
Flush.
Flush, maybe that's it. Yeah, someone look that up if you can. Well, I guess.
You already have seen that clear.
What's that? Let me like see. No input file stream, I don't want that. So CN is an instance of input stream here. And see, this is fail, I was using that. Set the error state flags. See, anybody see it yet? Is it clear? How do we empty it? Set state. Sets a new value for the stream's internal error state flags. Do you have an example here?
It's reading from file, isn't it? This is typing it in.
Anyway, you get the idea. You'll have to look this up. But basically, you have to modify this input stream object. So I don't want to get into that anymore.
Yeah, Nestor. Gosh.
Unless we want to get to the bottom of it here. So this set state, maybe that's it. Set state, clear the state. So we looked at this one already. And
But isn't that clear just for reading into a file, not for CN?
no, because the standard input stream is and file input are at this level are the same thing. So CN is the same thing. Let me. They're both instances of the same parent class. Let me see if I can find. Well, you know, I don't want to take any more time on that. So it's 1 o'clock already. Actually, let's stop. So I think that's it for today. But I have a teaching